Okay, guys, welcome. Today we're going to talk about logarithmic scales, and specifically we'll focus on earthquakes, sounds, and acids. Now, first we'll talk about earthquakes. So the earthquake magnitude scale is defined so that each magnitude represents about 32 times as much energy as the prior magnitude, right? So you're not increasing sort of linearly from one magnitude to the next, but by a factor of 32. Now, more technically, the magnitude m is related to the released energy E by the following equivalent formulas. We can either say that the log of the energy is equal to 4.4 plus 1.5 times the magnitude, or that the energy is equal to 2.5 times 10 to the 4, and then times 10 to the 1.5 m. Okay. Now, the energy is measured in joules, and magnitudes have no units. We just say that that's the magnitude. So in this first example, using the formula for earthquake magnitudes, calculate precisely how much more energy is released for each one magnitude on the earthquake scale, and then we'll also find the energy for 0.5 change in magnitude. Okay, so first of all, we're going to look at our formula for E, which will give the energy of the earthquake, which is 2.5 times 10 to the 4 times 10 to the 1.5 m. Okay, so now first we have that this first part here, oh, so I'm missing an m. This first part here is never going to change regardless of what m is, right? So of course the magnitude only is appearing in the second term. So now what we can do is, if we're going to look at the change, for example, let's look at when m is equal to 1 versus when m is equal to 2. Now, when m is equal to 1, we get that the energy is this 2.5 times 10 to the 4, and then we get times 10 to the 1.5 times 1, which is just 1.5. Then in the next one, we would get 2.5 times 10 to the 4 times 10 to the 1.5 times 2, which would be now to the third, right? So what's happening here is the first one, when m equals 1, we're going to get 2.5 times 10 to the 5.5, right, once we add those exponents. And for m is equal to 2, we're going to get 2.5 times 10 to the 7. And of course, the only thing that's going to change is this factor of 10, and it's going to go up by 1.5 each time. So for each magnitude increase, you're getting a factor of 10 to the 1.5 more joules of energy. Right? So, of course, what is 10 to the 1.5? Well, 10 to the 1.5, if we put that into the calculator, would give you about a 31.62. So each time you go up in magnitude, you're about, if you round up, 32 more times intense as the previous one. Right? So now, of course, if you were to do the same thing for a 0.5 change in magnitude, right? For example, you would go from 2.5 times 10 to the 4, and we'll go from 1 to 1.5 so that we have 10 to the 1.5. And then we'll go to 2.5 times 10 to the 4 times 10. Now to the 1.5 times 1.5, which would be 2.5 times 10 to the 4 times, let's see, and I guess this would be a 10 to the 2.25, I believe. No, not times, no, yeah, times 1.5, yep. So then we'll get a 2.25. So now if you look at this, this change here, you're going up by 10 to the 0.75, right? And if you increase by 10 to the 0.75, we're going to get about a 5.62 times more intense. Right. So that's sort of highlighting the difference between going up by a factor, not by a factor, by a magnitude of 1 or a magnitude of 0.5. Okay. Now in example 2, we have that the 1989 San Francisco earthquake, in which 90 people were killed, has magnitude 7.1. We'll calculate the energy that was released in joules. Well, of course, the energy released in joules, same formula as before, is 2.5 times 10 to the 4 times 10 to the 1.5 m. Okay, so if we plug in now for m equals 7.1, we're going to get 2.5 times 10 to the 4 times 10 to the 1.5 times 7.1. So if we multiply 1.5 times 7.1, 1.5 times 7.1, we're going to get that we have a 2.5 times 10 to the 4th times 10 to the 10.65. Right, so it looks like we're going to get a 2.5 times 10 and then to the 14.65. So this is the energy that was released for that San Francisco earthquake. Now, compare the energy of this earthquake to that of the 2003 earthquake that destroyed the ancient city of Bam, Iran, which had magnitude 6.3 and killed an estimated 50,000 people. Okay, so in 2003 earthquakes, this was 1989. All right, and I wonder if this was supposed to be BC or something, I don't know. But okay, so in 2003, we have that E, again, is equal to 2.5 times 10 to the 4th. Now this time it's 10 to the 1.5 times 6.3. All right, so we'll get a 2.5 times 10 to the 4th times 10 to the whatever 6.3 times 1.5 is. And if we do that, it looks like we're going to get a 10 to the 9.45. So 2.5 times 10 to the 13.45. Right. So those are the energy comparisons between these two earthquakes. And notice that even though one was only 0.8 magnitude smaller, you're getting this factor of 10 to the 1.2 of a difference in the amount of energy. Right. So over 100 times intensity difference there. Okay. So now the next type of logarithmic scale that we'll talk about is the decibel scale for sound. Now, the loudness in decibels is defined by the following equivalent formulas, where we have that the loudness in decibels is 10 times the log of the ratio of the intensity of the sound that we're interested in over the intensity of the softest audible sound. And we can also think of this as the ratio of the intensity of sound and the intensity of the softest audible sound is equal to 10 to the decibels divided by 10, right? So either one of these formulas are equivalent. Okay. So now in this next example, we're going to suppose that a sound is 100 times as intense as the softest audible sound, and we want to know what is its loudness in decibels. Okay. So what we need, since we're looking for the loudness in decibels, is the first formula. We want that the decibels is equal to 10 times the log of the intensity of the sound over the intensity of the softest audible sound. Now, since we're given that the sound is 100 times as intense as the softest audible sound, we know that the inside of this parentheses is just going to be able to be replaced with a 100. Right? So if we plug this in, we're going to get log of 100, so 10 times log of 100, and log of 100 would just be 2. So we're going to get that this is going to result in a 20 decibel sound, right? And just for a frame of reference, a 20 decibel sound is something like a whisper, right? So even though it's 100 times as intense as the softest audible sound, we're only going to get the loudness of about what a whisper is. Okay. Now in the next example, how does the intensity of a 57 decibel sound compare to that of a 23 decibel sound, right? So of course, we can use now this second formula for the decibels to compare the two sounds, right? So the second formula was that the intensity of the sound over the intensity of the softest audible sound is equal to 10 to the decibels scale over 10, right? So of course, for this one, what we have is that we're going to get that if we substitute 57 decibels for sound 1, and then we look at the 23 decibels for sound 2, right? If I say that this is one sound and then another one, would be sound 2 over the intensity of the softest audible sound. Finally, this equals 10 to the decibels over 10. And if I divide these two equations, what I'm going to be left with is the intensity of sound 1 over the intensity of sound 2, right? Because if you look at your two of these fractions and you do keep, change, flip, well, the intensity of the softest audible sounds will cancel and you'll get intensity of sound 1 over intensity of sound 2. Then this is going to equal, by your rules for dividing exponents, 10 to the decibels of sound 1 minus the decibels of sound 2 all over 10. So now if we plug this stuff in, we're going to get that our right side is going to be 10 to the 57 minus 23 over 10, which of course is going to give us 10 to the 34 over 10, which if we plug into the calculator here is going to give us 2512, right? So this means that if you have a 57 decibel sound, it's going to be 2,512 times as intense as a 23 decibel sound. Okay, so that's this example here, right? So we're comparing the intensities of two sounds here. Now, one final comment here for sounds is the inverse square law for sound. Now, the intensity of sound decreases with the square of the distance from the source. So this means that the intensity is proportional to 1 over d squared, where d is the distance. So we therefore say that sound follows an inverse square law with distance. So now in this next example, we're going to find out how far should you be from a jet to avoid a strong risk of damage to your ear. And of course, I'm copied the relevant things from the table that we'll need. Now, a jet at 30 meters is 140 decibels, and it's 10 to the 14th times as loud as the softest audible sound. But there's a strong risk of damage to the ear for a 120 decibel sound, and that is 10 to the 12th times as intense as the softest audible sound. So what we need to do is we need to figure out, well, how far should we be in order for this to avoid this amount of damage, right? So what we're going to do is we're going to use the similar approach as the last problem, right? So we're going to look at the ratio of the intensity of these two sounds. Right? So the ratio of the intensity of these is 10 to the 140 over 10 over 10 to the 120 over 10, which of course would give you a 10 to the 14th over 10 to the 12th, which would give you 10 squared, which is 100. Right? So that means that the jet is 100 times more intense than what strong risk of damage to the ear would be, right? So we need to be further from this jet to weaken the sound intensity by at least a factor of 100. So now, because sound follows the inverse square law with distance, if we move 10 times as far away, well, then we would get 1 over 10 squared, which is 1 over 100, right? Which is what we want. So we would need to move 10 times as far away. And since this is a jet at 30 meters, and I need to multiply that by 10, then I need to move at least 300 meters from the jet in order to be safe. All right, so that's the sort of the inverse square law with distance in work there. Okay, now the last thing that we'll discuss here is the pH scale, which is used to measure the acidity of liquids, right? So the pH scale is defined by the following equivalent formulas. We have that the pH is equal to minus the log of H plus, or we have that H plus is equal to 10 to the minus pH. Now, H plus is the hydrogen ion concentration in moles per liter. And a couple of things that we can note here is that pure water is neutral and has a pH of 7. Acids have a pH that's lower than 7, and bases have a pH that's higher than 7. So in this next example, we want to know what is the pH of a solution with a hydrogen ion concentration of 10 to the minus 12 moles per liter, and we'll use that to determine if it's an acid or a base, right? So of course here we would want to use the first version of the formula because we want to find the pH, and the pH is equal to minus the log of H plus. Well, here H plus is 10 to the minus 12. So if we do this, if we take minus log of 10 to the minus 12, we're going to get a positive 12, right? So then since the pH is 12, of course the pH being 12 is more than 7, that means that this is a base, right? So sort of like the opposite of an acid. Now in this next example, we have that in terms of hydrogen ion concentration, we're going to compare the acid rain with a pH of 2 to ordinary rain with a pH of 6, okay? So for acid rain, And of course, for this, we're going to use the other formula, right? We have that H plus is equal to 10 to the minus pH. So for acid rain, we get that H plus is equal to 10 to the minus pH, so to the minus 2. So we're going to get 1 over 100. And of course, this is in moles per liter. And then, of course, for the ordinary rain, we have that H plus is equal to a 10 to the minus pH, so minus 6. So this is 1 over 1 with 6 zeros, which is known as 1 million. And then, of course, this is moles per liter. All right, so those are the different hydrogen ion concentrations for each of these two, right? So now we can finally say that if we compare these two, if we look at the acid rain over the ordinary rain, if we do 10 to the minus 2 over 10 to the minus 6, using your exponent rules, you're going to get this is 10 to the 4th, right? Which is 10,000. So this is going to allow us to say that acid rain is 10,000 times more acidic than ordinary rain. Right? So that's that example. Okay, now that concludes this video on logarithmic scales. I hope you enjoyed, and I will see you next time.